All right, folks, we are in Chapter 6, Normal Distribution. This is Section 6-3. This is video recording number 3. All right, if you're following along in the book, which I hope you are, for the 10th edition, this is page 346 still. Okay, so the central limit theorem. So the central limit theorem is the third property of this sampling distribution of the x-bars. Okay, so the central limit theorem talks about the shape of the distribution. What does it look like? See, before we had a couple of properties up here in this blue box. We had a couple of properties. We learned about what the mean was, and we talked about what the standard deviation is, but we did not talk about the shape. So here we go. Here's the shape. This sample size, previously we had the 2 students, we also had the 30 adult males tested for triglycerides. As that sample size gets bigger and bigger without limit, in other words, it just keeps on going, gets bigger and bigger, in the limit, the shape of the distribution of the sample means, so the shape of the distribution of the x-bars, it has to be taken with replacement from a population with mean mu and standard deviation of sigma will approach. In other words, it gets closer and closer as n gets larger and larger. As the sample size gets larger and larger, it approaches a normal distribution. Okay, so what's the distribution? It's not the population, It's not the distribution of the population. It's the distribution of the x-bars. So think about that for 1 second here. We're not talking about the population, what the distribution of the population is. We're talking about what is the distribution of the x-bars. And it's going to get closer and closer to looking like a normal distribution. And since it's a normal distribution, we always are concerned about what the mean is and what the standard deviation is. Well, here it is. Just like we talked about previously, this normal distribution will have a mean of mu and it will have a standard deviation of sigma divided by the square root of n. So remember that sigma, that's the sigma of the original population, and n is the sample size. So let's have you have a sample size of 100. The square root of 100 is 10. So sigma divided by 10 is going to be a smaller number. So what it's saying is that the standard deviation for the normal distribution of the x-bars is more compact. It's narrower. And I think we have a picture coming up that's going to show that to us, okay? Okay. If the sample size is sufficiently large, if you have a large enough sample size, then the central limit theorem can be used to answer questions about sample means, the same way we did before, okay? And you'll see an example or two coming up where this is very important. We want to be able to talk about the x-bars. Many things in life, many things in science and sociology and psychology and so forth, we don't care about the individual data points as much as we care about the sample means. We care about the x-bars more than we care about the individual data points. Okay, so now the only difference is that when we're talking about the sample means, when we're talking about the x-bars, we're gonna do the same thing as we did before. We have the x-bars. They're considered as a random variable. That's our raw data. That's our original data. That's our x's, so to speak, our original random variable. We are going to do that mapping. We're going to convert those original random variables, we're going to convert them to z variables or z scores, okay? Z values is what he calls it, okay? Well, how do we do it? Well, z is equal to, this is exactly what we had before. The original data point, okay? The original data point that we started with, in this case is the x-bar, take away mu, that's the mean, divided by this guy down here, which I always think of the denominator as being kind of like a yardstick. It's telling you what kind of a yardstick are you dealing with here. Okay, all right. I'll let you read this for yourself. I think it's pretty clear. Okay. Okay, now this is confusing here. If a large number of samples of a given size are selected from a normally distributed population, or if a large number of samples of a given size that is greater than or equal to 30 are selected from a population that is not normally distributed, and the sample means are computed, then the distribution of sample means will look like the one we see right here in 6-33. Okay? Okay, so now that a little bit awkward here, the electronic version of the book, has this figure right here. In the textbook, in the paper, this figure comes after this. Okay, so I don't know what to tell you. If I were in your shoes, I'd be looking at the book. In any event, this paragraph right here, what in the heck does this mean? It is so freaking confusing, right? Okay, but it's not as hard as it looks. He spells it out right here. It is important to remember two things when you use the central limit theorem. Okay, so now he spells it out. It's a lot more clear than the paragraph right here. Okay, there's only two possibilities. When the original variable is normally distributed, so you start with something that's normally distributed, the x bars will be normally distributed, and it doesn't make any difference what the sample size is. Okay, so easy peasy, not a problem whatsoever. If it starts out, the original variable is normally distributed. If the original variable is not normal, then and only then you must have a sample size of 30 or more in order to use a normal distribution to approximate the distribution of the sample means. Okay, and then of course the larger the sample, the better the approximation will be. Okay, now this cartoon here is similar to what we had before. It's a normal distribution. The mu is right here. What do we have here? Mu plus 1 standard deviation, mu plus 2 standard deviations, and so forth. But this time the standard deviation is the standard deviation of the x bars. And just to torture you, this standard deviation of the x bars, we have a special name for it. We call it the standard error of the mean. And we saw that up here, right here. Hold on, here it is. The standard deviation of the sample mean, so the standard deviation of the x bars has this funny symbol here, is called the standard error of the mean. Now there's no particular reason why we do that. That's just the way we do it, okay? Just to torture you. Okay, so it's a new name, but it's the same exact concept. So if you look back at some of the previous cartoons that we had of the normal distribution, it wasn't as narrow as this one. So the author is trying to show you, hey, the x bars is more tightly concentrated. There's less dispersion than there is for the original variable. Okay, so remember, there's the original variable. That could be the heights of men. It could be the triglyceride levels of men, whatever it happens to be. The original variable has its own distribution. This is a distribution of the x bars. Okay, so let's take an example or two. And gosh, these examples really, I'm not happy about these examples. They seem so stupid and so boring, but just trust me on this. It's a very important concept. Okay, so the standard normal distribution, this is talking about how the standard normal distribution can be used to answer questions about the sample means. Okay, so example 613. How many hours do kids watch television? Okay, so kids between certain ages watch an average of 25 hours of television per week. Assume the variable is normally distributed. The standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. Okay. All right, so now listen. The original variable, what he calls up here, the original variable is hours watched TV. So it's very important. I'm going to really stress this to you. It's very important to always be able to clearly articulate, be able to clearly state what is the random variable. If you can't do that, you're just going to be floundering on these problems. So the original variable, the original random variable that we're dealing with here is hours watching TV. Okay? So that's the original variable. It says here they watch an average of 25 hours of television per week. So my mu is 25. Okay, it is normally distributed, and the standard deviation is 3 hours. So now I have everything I need to know. I've got the mu, I've got the standard deviation, and I've got my n being the sample size. Okay, so now I'm talking about 20 kids that I select from this population. I randomly select them. Now I'm interested in what's the probability that the mean of the number of hours that these kids watch. So like you got 20 kids, you find their mean. What's the probability that mean, that X bar, is greater than 26.3? Okay, seems like a reasonable question, right? Now, you may not be interested in the kids watching TV, but this could easily be adapted to where instead of talking about kids watching TV, we could be talking about how long people live if they take a certain medication. So you can see where this has really, really important applications. In fact, let me just kind of wing it here. I missed doing this in real time here. Let's just change this just to show us how important this can be. We're all sitting at home now because of the quarantine for COVID virus, right? What if we were to say that on average it takes 25 hours from the moment of exposure? It takes 25 hours for you to start showing symptoms. Okay, suppose it's normally they decide, okay, it's normally distributed. They decide the standard deviation is 3 hours. You take 20 people who have been exposed, and you want to find out what's the probability that instead of being exactly 25 hours, that their onset of their symptoms is greater than 26.3 hours. Now that may sound like a made-up example, but you can see how somebody that's involved with this sort of thing, they may want to know. They may want to know, well, after you get exposed, how much time does it take before you start showing the symptoms? So again, it's there's plenty of examples, and I hope you'll take my word for it. This stuff is important. Okay, so now it says that the original variable, is approximately normally distributed. That was, it didn't say approximately, it said it is. Okay, so let's assume that this word approximately doesn't seem to fit there. But so since the variable is normally distributed, the distribution of sample means will be approximately normal with a mean of 25. Okay, so I don't want to be pedantic here, but he's saying here, he's talking about it being approximately, he says it's approximately normal. And then up here, he says, hey, wait a second, if it's normally distributed, the distribution of the X bars will be normally distributed. So why all of a sudden are we talking about, why are we talking about it being approximately normal? The only thing I can think about, the only thing I can come up with is that in the theorem itself, it says this theorem only works as the sample size n increases without limit. So if it's anything less than, a bazillion, everything's approximate. I guess that's why he said. I'm not 100% sure. Okay, so in any event, for our purposes, we're going to say it's normally distributed, and it has a mean of 25, standard deviation of the sample mean. So remember the sample means, that's the X bars. So the distribution of the X bars is this. Okay, there's the number. So you draw the normal curve just exactly like we did before. Okay, you find the z value. Okay, find the corresponding area and to the area to the right. Okay, so it's 2.62%. So therefore we can come up with this conclusion. So you work your way through that. I hope I helped you there, but that's what's going on these things, and that's the end of this tape.